The universe stretches before us in stillness, vast and measured. Its architecture written in light that has traveled for billions of years to reach our eyes. In the silence of space, structures emerge that dwarf our imagination, patterns that speak to forces and events we are only beginning to understand. If you have not yet subscribed, consider doing so now and watch in full screen to fully appreciate what follows. What the James Webb Space Telescope has revealed in recent observations is a structure so immense, so unexpected in its coherence and scale, that it challenges our models of how the cosmos organizes itself across the largest distances we can observe. A wall of galaxies stretching across the sky, not as a metaphor, but as a physical alignment of luminous matter, a coherent feature spanning hundreds of millions of light years, possibly more, detected with unprecedented clarity in the infrared bands where Webb excels. This is not a singular galaxy, not a cluster, not even a supercluster in the traditional sense, but a wall, a sheet, a filament of such extent that it appears to bridge vast regions of the observable universe, and its discovery prompts us to revisit everything we thought we understood about cosmic structure, the distribution of matter, and the processes that shaped the universe from its earliest moments to the present day. To understand what James Webb has found, we must first understand what we mean by a wall of galaxies and why such a structure is significant. The universe is not uniform. Matter is not distributed evenly across space. Instead, galaxies gather into groups, groups into clusters, clusters into superclusters, and superclusters into filaments and sheets that outline vast voids where almost nothing exists. This cosmic web, as it is called, is the largest known structure in the universe, a network of matter tracing the underlying distribution of dark matter, shaped by gravity over billions of years. The filaments are the densest parts of this web, and where filaments intersect or align, we find walls, immense surfaces populated by thousands or even tens of thousands of galaxies, all moving together, all sharing a common history written in the expansion of space itself. The wall observed by James Webb is one such structure, but its scale, its clarity, and the distance at which it has been observed make it unique. It is not simply large, it is coherent, meaning the galaxies within it are not randomly scattered but aligned, suggesting a shared formation history, a common environment and physical processes that operated across unimaginably large scales during the early universe. James Webb Space Telescope, unlike its predecessor Hubble, observes primarily in the infrared spectrum. This is crucial. Infrared light penetrates dust, reveals heat, and most importantly for cosmology, captures light from the most distant objects in the universe. As the universe expands, light from distant galaxies is stretched, redshifted, its wavelengths lengthened from visible light into the infrared and beyond. The farther away a galaxy is, the faster it is receding due to the expansion of space, and the more its light is redshifted. Webb's instruments are designed to detect this redshifted light, allowing it to see galaxies as they were billions of years ago, closer to the Big Bang, when the universe was younger, hotter, and denser. The wall of galaxies detected by Webb exists at a significant redshift, meaning it is distant both in space and in time. When we observe this structure, we are not seeing it as it is now, but as it was when the universe was a fraction of its current age. The light from these galaxies has been traveling toward us for billions of years, and what Webb has captured is a snapshot of the universe's large-scale structure at an epoch when such structures were still forming, still coalescing under the influence of gravity, dark matter, and the initial conditions set by the Big Bang itself. The discovery of this wall was not instantaneous. It emerged from deep field observations, long exposures capturing faint light from distant regions of the sky, combined with spectroscopic analysis to measure redshifts and determine distances. Webb's near-infrared camera, and NIR-CAM, and its spectroscopic instruments allowed astronomers to map the three-dimensional distribution of galaxies across a portion of the sky, revealing not just their positions on the celestial sphere, but their distances, their velocities, their places in cosmic time. What appeared at first as a clustering, a concentration of galaxies in a particular direction, resolved into something more structured as redshift data accumulated. The galaxies were not merely grouped, they were aligned, forming a coherent sheet extending across hundreds of millions of light years, possibly more depending on how the boundaries of the structure are defined. This alignment, this coherence, is what defines a wall. It is a two-dimensional surface embedded in three-dimensional space, a vast plane of galaxies tracing a filament or the intersection of filaments in the cosmic web. The wall is not solid, not continuous in the sense of being filled with matter everywhere, but rather populated by galaxies at varying densities, with higher concentrations along certain lines and nodes where filaments cross or merge. Yet, from a cosmological perspective, it behaves as a single structure, a feature of the large-scale distribution of matter, a result of the same gravitational processes that formed clusters and superclusters everywhere in the universe. To appreciate the significance of this wall, we must delve into the physics of structure formation, beginning with the early universe. Immediately after the Big Bang, the universe was extremely hot and dense, a plasma of particles and radiation in thermal equilibrium. As it expanded and cooled, matter began to clump under the influence of gravity, but not uniformly. Tiny fluctuations in density, quantum fluctuations blown up to cosmic scales during inflation, seeded the formation of all structure. Regions slightly denser than average attracted more matter, grew denser still, and eventually collapsed into the first stars, galaxies, and clusters. But this process did not happen in isolation. Dark matter, which does not interact with light but exerts gravitational influence, dominated the mass budget of the universe and formed the scaffolding upon which visible matter accumulated. Dark matter halos formed first, and within these halos, gas cooled and condensed to form stars and galaxies. Over time, these halos merged, grew, and organized into larger structures, following the hierarchical model of structure formation. Small halos merged into larger halos, which merged into clusters which aligned into filaments and walls. The cosmic web we observe today is the result of billions of years of this hierarchical growth, driven by gravity, modulated by dark energy, and shaped by the initial density fluctuations imprinted during inflation. The wall observed by Webb represents a snapshot of this process at a time when the universe was younger. The redshift of the structure places it at a look-back time corresponding to billions of years in the past, a time when the universe was more compact, when structures were less evolved, and when the processes of merging and growth were still actively shaping the large-scale distribution of matter. At such distances, we expect to see the cosmic web in an earlier state, with filaments and walls perhaps less pronounced, less massive, less populated than in the nearby universe. Yet what Webb has found is a wall of remarkable coherence and extent, suggesting that large-scale structures formed earlier and more robustly than some models predicted. This is not necessarily in conflict with the standard cosmological model, the lambda-cold dark matter model, which has been remarkably successful in explaining the observed universe, but it does push the boundaries of what we expect to see at such epochs. It raises questions about the efficiency of structure formation, the role of dark matter in the early universe, the influence of dark energy, and the initial conditions set by inflation. A wall this large, this coherent, requires that the underlying density fluctuations were strong enough, extended enough, and aligned in such a way that gravity could pull together vast amounts of matter across immense distances, faster and more effectively than previously thought necessary. Let us now turn to the observational details, the methods by which this wall was detected and characterized. James Webb does not simply take pictures of the sky. It collects data, photons, each carrying information about its source. The light from distant galaxies is faint, dimmed by distance, redshifted into the infrared, and often obscured by intervening dust or contaminated by foreground sources. To isolate the signal from a distant structure, astronomers must use spectroscopy, breaking the light into its component wavelengths to measure the redshift precisely. Redshift is determined by identifying spectral lines, features in the spectrum corresponding to known atomic transitions, and measuring how much these lines have been shifted toward longer wavelengths. The amount of shift tells us the recession velocity of the galaxy, which combined with Hubble's law gives us the distance. By measuring redshifts for many galaxies across a region of the sky, Astronomers can construct a three-dimensional map, plotting the positions of galaxies not just in 2 dimensions on the sky, but also in depth, along the line of sight. This redshift survey technique is the foundation of large-scale structure studies. When applied to the region where the wall was discovered, the redshift data revealed that many galaxies, spread across a wide angle on the sky, shared similar redshifts, meaning they were all at roughly the same distance from us. This concentration in redshift space corresponds to a concentration in real space, a coherent structure extending across the sky at a specific epoch in cosmic history. The wall's extent is measured in Comoving coordinates, a coordinate system that accounts for the expansion of the universe. Because space itself is expanding, distances between objects grow over time, even if the objects are not moving through space. To make sense of large-scale structure, cosmologists use Comoving distance, which factors out the expansion and gives a measure of distance as if the universe were not expanding, or equivalently, as if we were measuring distances at a single moment in cosmic time. In Comoving coordinates, the wall spans hundreds of millions of light-years, possibly approaching or exceeding 1 billion light-years depending on how its boundaries are defined. This is comparable to the largest known structures in the nearby universe, such as the Sloan Great Wall or the Hercules Corona Borealis Great Wall, but the key difference is that Webb's wall is observed at a much greater distance, at a much earlier time, when the universe was younger and structures were supposed to be smaller and less developed. The existence of such a large structure at such an early epoch is what makes this discovery so intriguing. It suggests that the seeds of large-scale structure were sown very early, that the initial density fluctuations were sufficient to begin forming walls and filaments within the first few billion years after the Big Bang, and that the processes of gravitational collapse and merging were efficient enough to assemble coherent structures on these scales even in the young universe. To understand how a wall forms, we must consider the dynamics of gravitational collapse in an expanding universe. In the early universe, space was expanding rapidly, driven by the kinetic energy of the Big Bang, and later by dark energy. Matter was distributed almost uniformly, with only tiny fluctuations in density. As the universe expanded and cooled, these fluctuations began to grow. Regions that were slightly overdense attracted more matter, increasing their density further. Regions that were underdense lost matter to the overdense regions, becoming voids. This process is nonlinear. The rich get richer, and the poor get poorer. Overdense regions collapsed under their own gravity, forming bound structures like galaxies and clusters. Underdense regions expanded faster than the average expansion rate, becoming vast voids nearly devoid of matter. The boundary between these regions, the transition from overdense to underdense, forms the filaments and walls of the cosmic web. A wall is essentially a surface where matter has accumulated, a 2-dimensional sheet in 3-dimensional space, where galaxies are more densely packed than in the surrounding voids. The formation of a wall requires that the initial density fluctuations were elongated or aligned in a particular way, creating a sheet-like overdensity rather than a spherical one. Such alignments can arise naturally from the statistics of random fluctuations, especially when considering the correlation of fluctuations on different scales. Where multiple modes of fluctuation overlap constructively, you can get extended structures like filaments and walls. The larger the structure, the rarer it is because it requires fluctuations on very large scales, which are less common according to the power spectrum of initial fluctuations predicted by inflation. The power spectrum is a statistical description of the initial fluctuations, describing how the amplitude of fluctuations varies with scale. In the standard model, inflation predicts a nearly scale-invariant spectrum, meaning fluctuations on all scales have roughly similar amplitudes, with a slight tilt favoring smaller scales. This spectrum is imprinted in the cosmic microwave background radiation, the light from the early universe, and has been measured with extraordinary precision by satellites like WMAP and Planck. The power spectrum determines the statistical properties of large-scale structure, including the abundance of clusters, filaments, and walls. A wall as large as the one observed by Webb is a rare event, a statistical fluctuation on the tail of the distribution, but not impossible given the volume of the observable universe. However, if such walls are too common, or too large, or too coherent at high redshifts, it could indicate that the power spectrum is not quite what we thought, that there is more power on large scales than predicted, or that additional physical processes are at work enhancing structure formation. This is where the discovery becomes scientifically important, because it provides a test of our cosmological models, a constraint on the parameters that govern the universe's evolution, and potentially a hint of new physics beyond the standard model. Let us now explore the role of dark matter in forming this wall. Dark matter constitutes about 85% of the matter in the universe. It does not emit, absorb, or reflect light, making it invisible to telescopes, but it exerts gravitational force and is the dominant source of gravity on large scales. Dark matter formed the first structures in the universe, collapsing into halos well before ordinary matter could cool and form stars. These dark matter halos created gravitational wells into which ordinary matter, gas, fell and accumulated. The distribution of dark matter therefore determines the distribution of visible matter, the galaxies we observe. The cosmic web of filaments and walls is fundamentally a dark matter structure, with galaxies acting as tracers of the underlying dark matter distribution. The wall observed by Webb is likely a region where dark matter is concentrated, a filament or intersection of filaments in the dark matter web, and the galaxies we see are the visible component, the baryonic matter that has condensed within the dark matter halos. The coherence and extent of the wall suggest that the dark matter distribution in this region is also coherent and extended, which in turn depends on the initial conditions, the power spectrum of fluctuations, and the dynamics of dark matter collapse. Because dark matter is collisionless, it collapses differently than gas. Gas can shock, heat, and lose energy through radiation, allowing it to settle into dense cores. Dark matter cannot lose energy this way, so dark matter halos remain more diffuse, and their structure retains memory of the initial conditions and the history of mergers. By studying the distribution of galaxies in the wall, and inferring the underlying dark matter distribution, astronomers can learn about the formation history of this structure, the mass it contains, and the gravitational forces that shaped it. The wall's redshift tells us its distance and look-back time, but it also tells us something about the expansion history of the universe. Redshift is related to the scale factor, a measure of how much the universe has expanded since the light was emitted. A higher redshift means the light was emitted when the universe was smaller, denser, and younger. The relationship between redshift and distance depends on the cosmological parameters, including the Hubble constant, the matter density, and the dark energy density. By measuring the redshift distribution of structures like the wall, and comparing it with predictions from cosmological models, we can refine our estimates of these parameters. The existence of the wall, at its observed redshift, provides a constraint on the growth of structure over cosmic time, a test of how fast gravity can assemble matter into large-scale structures given the expansion rate and the matter content of the universe. If the wall is too massive or too extended for its redshift, it suggests that structure formation was more efficient than predicted, which could imply more matter, less dark energy, or different initial conditions than assumed. Conversely, if the wall fits comfortably within the predictions of the standard model, it provides confirmation that our understanding of cosmic evolution is on the right track. Let us delve deeper into the concept of redshift and cosmic time. Redshift is denoted by the letter Z, defined as the fractional change in wavelength of light. A redshift of Z equals 1 means the wavelength has doubled, Z equals 2 means tripled, and so on. The redshift of the wall, let us say, for the sake of discussion, it is around Z equals 2 or 3, though the exact value would depend on the specific observations, corresponds to a time when the universe was roughly 2 to 3 billion years old, depending on the cosmological model used. At this epoch, the universe was more compact, galaxies were younger, star formation was more vigorous, and the cosmic web was still actively assembling. Observing a coherent wall at such a redshift means we are seeing a structure that formed early, during a time when the universe was more dynamic, when mergers and interactions were more common, and when the large-scale distribution of matter was still being sculpted by gravity. The light from this wall has traveled for over 10 billion years to reach us, carrying information about the state of the universe when it was a quarter or a third of its current age. This light, now stretched into the infrared, is captured by Webb's detectors, analyzed by astronomers, and used to reconstruct the three-dimensional structure, the mass distribution, and the formation history of one of the largest coherent structures ever observed. The coherence of the wall is worth emphasizing. A random clustering of galaxies, even if dense, does not constitute a wall. A wall requires alignment, a preferred orientation, a sheet-like geometry. This coherence implies that the initial density fluctuations in this region had a particular shape, elongated along two dimensions and compressed along the third, creating a pancake-like overdensity. Such shapes can arise from the gravitational collapse of triaxial or sheet-like perturbations, which are common in the statistics of Gaussian random fields, the mathematical model used to describe the initial fluctuations. When such a perturbation collapses, matter flows along the shortest axis, compressing the sheet and increasing its density while leaving it extended in the other two dimensions. Over time, the sheet can fragment into filaments and clusters, but on the largest scales, the sheet-like geometry persists, and we observe it as a wall of galaxies. The more coherent the wall, the more aligned the galaxies within it, the more precisely we can infer the shape and amplitude of the initial fluctuation that gave rise to it. This makes walls like the one observed by Webb valuable probes of the initial conditions of the universe, the statistical properties of the fluctuations, and the processes that amplify those fluctuations into the structures we see today. Let us now consider the galaxies themselves within the wall. Each galaxy is a complex system, containing billions or trillions of stars, gas, dust, and dark matter, all bound together by gravity. Galaxies within the wall are not isolated. They interact with each other and with the larger environment. They experience tidal forces from nearby galaxies, they accrete gas from the intergalactic medium, they may undergo mergers with other galaxies, and they are influenced by the large-scale flow of matter along the filaments and into the wall. The environment within a wall is different from that in a void or in a rich cluster. Walls have intermediate densities higher than voids but lower than cluster cores. This affects the properties of the galaxies within them. Galaxies in dense environments tend to have less gas, less star formation, and older stellar populations, because interactions and ram pressure stripping remove the gas needed to form new stars. Galaxies in low-density environments, like voids, tend to be gas-rich, actively forming stars, and less evolved. Walls represent a middle ground, a transition region where galaxies are beginning to feel the effects of their environment, have not yet been fully processed by dense cluster conditions. By studying the properties of galaxies in the wall, their colors, their spectra, their star formation rates, their morphologies, astronomers can learn about how environment influences galaxy evolution, and how the large-scale structure shapes the populations of galaxies we observe. Webb's infrared sensitivity is particularly well suited to studying these galaxies. Infrared light penetrates dust, allowing us to see star formation that is obscured at visible wavelengths. Many galaxies at high redshift are dusty, their star formation hidden by clouds of dust that absorb ultraviolet and visible light and re-emit it in the infrared. Webb can detect this infrared emission, revealing the true star formation rates and stellar masses of these galaxies. Additionally, the rest frame optical light from high redshift galaxies is shifted into the infrared, so Webb is effectively observing these galaxies in their rest frame optical bands, where we can see features like emission lines from ionized gas, absorption lines from stars, and continuum emission that traces the stellar population. This allows detailed spectroscopic studies, measuring not just redshifts but also chemical compositions, ages, star formation histories, and kinematics of the galaxies within the wall. Such detailed studies were not possible with previous telescopes, which lacked the sensitivity and infrared capability of Webb. The discovery of the wall is therefore not just a discovery of structure, but an opportunity to study galaxy evolution in a specific environment at a specific epoch, providing insights into how galaxies grow and change over cosmic time. The wall also provides a laboratory for studying the intergalactic medium, the gas that fills the space between galaxies. This gas is mostly hydrogen, ionized by ultraviolet light from stars and quasars, and it traces the distribution of matter on large scales. The intergalactic medium is denser along filaments and walls, and its properties depend on the local density and the history of heating and ionization. By observing the absorption of background light by the intergalactic medium along lines of sight through the wall, astronomers can map the gas distribution, measure its temperature and density, and study how it evolves over time. This is done using quasar absorption line spectroscopy, where the spectrum of a distant quasar shows absorption features corresponding to intervening gas clouds at various redshifts. The distribution of these absorption features, known as the Lyman alpha forest, is a powerful probe of the intergalactic medium and the large-scale structure. A wall like the one observed by Webb should be associated with an enhancement in the Lyman alpha forest, a clustering of absorption lines at the redshift of the wall, indicating that more gas is present along that line of sight. By combining quasar absorption studies with galaxy redshift surveys, astronomers can build a complete picture of the matter distribution, both baryonic and dark, within the wall. Let us now turn to the implications of this discovery for cosmology. The Lambda Cold Dark Matter Model, LCDM, is the standard model of cosmology, successfully explaining a wide range of observations, from the cosmic microwave background to the large-scale structure to the expansion history of the universe. According to LCDM, the universe is dominated by dark energy, which drives accelerated expansion, and cold dark matter, which forms the scaffolding for structure. The model predicts the statistical properties of the cosmic web, including the abundance and sizes of voids, filaments, walls, clusters, and superclusters. The discovery of a large wall at high redshift is consistent with LCDM if it falls within the expected range of fluctuations, but if it is too large or too coherent, it could challenge the model. There is a tension in cosmology between observations on different scales. The cosmic microwave background observed by Planck gives us precise measurements of the cosmological parameters, including the amplitude of fluctuations on large scales. These measurements predict the amount of clustering we should see in the late-time universe in the distribution of galaxies and clusters. However, some observations of large-scale structure suggest slightly more clustering than predicted, a phenomenon sometimes called the sigma-8 tension, referring to the parameter that measures the amplitude of matter fluctuations on a scale of 8 megaparsecs. If the wall observed by Webb is statistically rare, requiring larger fluctuations than predicted by the Planck parameters, it could be evidence of this tension, suggesting that the early universe had more power on large scales than inferred from the microwave background, or that structure formation was more efficient due to some physical process not included in the standard model. Alternative explanations exist. One possibility is that the wall is not a single structure, but a projection effect, an alignment of multiple smaller structures along the line of sight that happen to have similar redshifts. Projection effects are common in astronomy, where three-dimensional structures are observed as two-dimensional images on the sky, leading to apparent associations that are not physically meaningful. To rule out projection effects, astronomers must carefully analyze the redshift distribution and the three-dimensional geometry of the structure, looking for coherence not just in redshift but in velocity space and in the correlation of galaxy properties. If the wall is a true physical structure, the galaxies within it should be moving together, sharing a common bulk velocity and showing correlations in their peculiar velocities, the deviations from the smooth expansion of the universe due to gravitational interactions. These peculiar velocities are small, typically hundreds of kilometers per second, but measurable with precise spectroscopy, and they provide a signature of the gravitational forces acting within the structure. Webb's spectroscopic capabilities, combined with large samples of galaxies, allow such measurements to be made, confirming whether the wall is a genuine coherent structure or a chance alignment. Another consideration is the role of dark energy. Dark energy affects the expansion rate of the universe and the growth of structure. In the early universe, when matter dominated, gravity was the primary force shaping structure, and overdensities grew steadily. As the universe expanded and dark energy became more significant, its repulsive effect began to counteract gravity, slowing the growth of structure. The transition from matter domination to dark energy domination occurred relatively recently, cosmologically speaking, around a redshift of 1 or so depending on the dark energy model. The wall observed by Webb, at a redshift of 2 or 3, formed during or before this transition, a time when structure growth was still robust but beginning to be affected by dark energy. The size and coherence of the wall depend on how fast structure could grow at that epoch, which depends on the amount of matter, the amount of dark energy, and the equation of state of dark energy, the relationship between its pressure and density. If dark energy behaves differently than a cosmological constant, if its equation of state changes over time, it could affect the growth of structure in ways that are observable. The wall, therefore, provides a constraint on dark energy models, a test of whether the cosmological constant is sufficient, or whether more complex models are needed. Let us also explore the initial conditions more deeply. The initial density fluctuations are thought to have been generated during inflation, a brief period of exponential expansion in the first fraction of a second after the Big Bang. Inflation stretches quantum fluctuations to cosmic scales, creating a nearly Gaussian, nearly scale-invariant spectrum of perturbations. These perturbations are the seeds of all structure. The properties of the inflationary epoch, such as the energy scale of inflation, the duration, and the shape of the inflationary potential, determine the detailed properties of the perturbation spectrum, including any deviations from scale invariance, any non-Gaussianities, and any features or bumps in the spectrum at particular scales. The existence of a large wall at high redshift provides a probe of the inflationary spectrum at large scales that are difficult to probe with a cosmic microwave background alone because the largest observable scales are limited by the size of the observable universe at the time of recombination. By studying the abundance and properties of the largest structures, like the wall observed by Webb, we can extend our tests of inflation to larger scales, looking for deviations from the predictions of the simplest inflationary models. If the wall is larger or more coherent than expected, it could indicate a deviation from scale invariance, more power on large scales, or a feature in the inflationary spectrum that enhances fluctuations at the scale corresponding to the wall's size. Such features could arise from specific inflationary models, providing a way to distinguish between different theories of the very early universe. The wall's discovery also has implications for our understanding of cosmic variance. Cosmic variance is the statistical uncertainty in measurements of the universe due to the fact that we observe only one realization of the statistical ensemble. The universe is a single random draw from a distribution of possible universes, all consistent with the same initial conditions and physical laws, but differing in the details of how fluctuations are realized. Because we observe only one universe, we cannot average over many realizations to reduce statistical noise. This is especially problematic on large scales where the number of independent samples is small. A structure like the wall occupies a significant fraction of the observable volume at its redshift, meaning it represents a rare event, and its existence increases the cosmic variance, the uncertainty in our estimates of cosmological parameters derived from large-scale structure observations. If such walls are more common than expected, it suggests that the universe is more inhomogeneous on large scales than we thought, which could bias our measurements and require adjustments to our models. Understanding the statistical significance of the wall, whether it is a 3 sigma event or a 5 sigma event, is crucial for assessing its implications. A 3 sigma event is unusual but not unexpected in a large survey. A 5 sigma event would be highly surprising and demand new physics or a revision of our assumptions. Let us now consider the wall in the context of other known large-scale structures. The nearby universe contains several notable walls and filaments. The Sloan Great Wall, discovered in data from the Sloan Digital Sky Survey, is a vast structure stretching over 1 billion light-years composed of thousands of galaxies organized along a filamentary network. The CFA2 Great Wall, discovered earlier in the Center for Astrophysics Redshift Survey, is another prominent structure in the local universe. These structures are observed at low redshift, meaning we see them as they are relatively recently within the last few billion years. The wall observed by Webb is at much higher redshift, meaning it is much older, seen as it was when the universe was younger. Comparing the properties of high redshift and low redshift walls allows us to study the evolution of large-scale structure over cosmic time, tracking how walls grow, how their galaxy populations change, and how they are affected by the expansion and dark energy. If the high redshift wall is similar in size and coherence to low redshift walls, it suggests that large-scale structure forms early and evolves slowly, with the basic architecture of the cosmic web established within the first few billion years. If the high redshift wall is smaller or less coherent, it suggests that walls grow over time, accreting more galaxies and extending as filaments merge and matter flows into the structure. Webb's observations provide a snapshot of a wall at an earlier stage of its evolution, a comparison point for understanding the growth history of the largest structures in the universe. The discovery of the wall also raises questions about the homogeneity of the universe on the largest scales. The cosmological principle, a foundational assumption in cosmology, states that the universe is homogeneous and isotropic on sufficiently large scales, meaning it looks the same in all directions and at all locations when averaged over large enough volumes. This principle is supported by the isotropy of the cosmic microwave background, which shows that the early universe was remarkably uniform, with fluctuations of only 1 part in 100,000. However, the existence of large structures like the wall suggests that the universe is not perfectly homogeneous on all scales. There is a scale called the homogeneous scale, above which the universe becomes statistically uniform. Current estimates place this scale at a few hundred megaparsecs, but the discovery of structures approaching or exceeding 1 billion light-years in size challenges this estimate. If walls and filaments extend to larger scales than previously thought, the homogeneity scale may be larger, which could have implications for our interpretation of cosmological observations and our ability to apply the cosmological principle. Some researchers have proposed that the universe may never become perfectly homogeneous, that structure continues to all scales, forming a fractal-like pattern. While this idea is controversial and not supported by most observations, the discovery of very large structures like the wall keeps the question open and motivates further study of the largest scales observable. Let us now return to the observational techniques and consider the challenges involved in detecting and characterizing the wall. Observing faint, distant galaxies requires long integration times, even for a telescope as powerful as Webb. Each galaxy emits only a tiny amount of light, and that light is spread over a large area of the detector, diluted by the expansion of space and dimmed by distance. To build up enough signal to detect a galaxy and measure its spectrum, Webb must stare at the same patch of sky for hours or even days, accumulating photons one by one. This is done in deep field surveys, where a small region of the sky is observed repeatedly with long exposures, maximizing the sensitivity and allowing the detection of the faintest objects. The wall was likely discovered in such a survey, a deep field covering a region of sky large enough to capture a significant portion of the structure. The field must be large enough to see the extent of the wall to map its boundaries and measure its size, but not so large that the observations become prohibitively expensive in terms of telescope time. Balancing depth and area is a key trade-off in survey design, and the discovery of the wall likely represents an optimal balance, a field deep enough to reach the high redshift of the structure and wide enough to capture its full extent. Spectroscopy is more time-consuming than imaging. Taking an image captures light from all objects in the field simultaneously, but measuring a spectrum requires dispersing the light and recording the intensity at each wavelength, which takes more photons and more time. Webb's spectroscopic instruments, the near-infrared spectrograph NIRSpec and the mid-infrared instrument MIRI, use techniques like multi-object spectroscopy and integral field spectroscopy to observe many objects at once, improving efficiency. Multi-object spectroscopy uses a device like a microshutter array, where individual shutters can be opened or closed to allow light from specific objects to pass through while blocking light from others, enabling the telescope to take spectra of hundreds of objects simultaneously. Integral field spectroscopy captures a spectrum at every point in a two-dimensional field, creating a data cube with two spatial dimensions and one spectral dimension, allowing detailed studies of extended objects or dense fields. These techniques have enabled Webb to conduct large spectroscopic surveys, measuring redshifts for thousands of galaxies in a single field, building up the three-dimensional maps needed to discover and characterize structures like the wall. The data processing is also complex. Raw data from Webb must be calibrated, corrected for instrumental effects, cleaned of cosmic rays and other artifacts, and then analyzed to extract scientific information. Spectra must be extracted from the two-dimensional detector images, wavelength calibrated, flux calibrated, and then analyzed to identify spectral lines and measure redshifts. This requires sophisticated software, algorithms, and expertise, and it is an area where errors can creep in. Misidentifying a spectral line, for example, can lead to an incorrect redshift, placing a galaxy at the wrong distance and distorting the three-dimensional structure. Careful cross-checks using multiple lines, comparing with photometric redshifts, and looking for consistency in the velocity structure are essential to ensure the reliability of the results. The discovery of the wall represents not just the power of Webb's hardware, but also the skill of the teams that designed the observations, processed the data, and analyzed the results, extracting meaningful scientific conclusions from terabytes of raw data. Let us delve deeper into the physical processes that govern the formation and evolution of the wall. Gravity is the dominant force on large scales, pulling matter together, causing overdensities to grow and underdensities to expand. But gravity alone does not determine the structure. The initial conditions, the spectrum of fluctuations, set the stage. The expansion of the universe provides a time-varying background against which gravity acts. Dark energy opposes gravity, slowing the growth of structure. Baryonic physics, the behavior of gas and stars, adds complexity. Gas can shock, heat, cool, form stars, and be expelled in winds and supernovae, all of which affect the distribution of matter and the properties of galaxies. On the scales of the wall, baryonic physics is less important than gravity and dark matter, because the structure is so large and diffuse that gas pressure and other baryonic effects are negligible compared to gravitational forces. The wall is a gravitational structure, shaped primarily by dark matter and the expansion of space, with galaxies as tracers of the underlying mass distribution. However, baryonic physics does matter for understanding the galaxies within the wall, their star formation, their colors, their spectra, and their evolution over time. The interplay between gravity and baryonic processes creates the diversity of galaxies we observe, from massive ellipticals to star-forming spirals to dwarf irregulars, all coexisting within the same large-scale structure. The dynamics of the wall can be understood in terms of gravitational instability. A small overdensity in the initial conditions grows over time as matter is attracted to it. The growth rate depends on the expansion rate of the universe and the matter content. In a matter-dominated universe, overdensities grow as the scale factor, meaning they double in density as the universe doubles in size. In a dark energy-dominated universe, the growth slows and eventually stops as dark energy's repulsive effect overcomes gravity. The wall formed during the transition between these regimes, a time when growth was still rapid but beginning to slow. The shape of the overdensity, sheet-like in the case of a wall, determines how matter flows and how the structure collapses. For a sheet, matter flows along the short axis, compressing the sheet into a thinner, denser structure, while the sheet remains extended along the other two axes. This is called pancake collapse, a term from Russian cosmologist Yakov Zeldovich, who first analyzed the collapse of non-spherical perturbations. Zeldovich showed that perturbations collapse first along their shortest axis, forming pancakes, which then fragment into filaments, which then fragment into halos. The cosmic web is a manifestation of this hierarchical collapse, and walls like the one observed by Webb are the pancakes. the sheet-like structures that form in the first stage of collapse. The wall is not static. It is evolving, growing, accreting matter from surrounding regions, and being deformed by the gravitational influence of nearby structures. Galaxies within the wall are moving, both with the expansion of space and with peculiar velocities induced by local gravitational fields. These peculiar velocities cause galaxies to stream along filaments toward clusters, creating a pattern of infall and accretion that shapes the structure over time. The wall may also be interacting with other structures, merging with nearby filaments or walls, forming nodes where multiple structures intersect. These nodes are the sites of the richest clusters, where the density is highest and the gravitational potential is deepest. By studying the velocity field within and around the wall, astronomers can map the gravitational forces, infer the mass distribution, and predict the future evolution of the structure. Over time, the wall will continue to accrete matter, its galaxies will continue to evolve, and the structure will become more prominent, more massive, and more complex, eventually resembling the great walls we observe in the nearby universe. Let us now consider the wall in the context of cosmic time and the history of the universe. The universe began with the Big Bang, a moment of infinite density and temperature, or at least a state so extreme that our current physical theories cannot describe it. From this beginning, the universe expanded and cooled, passing through distinct epochs. The first fraction of a second saw inflation, the rapid exponential expansion that smoothed the universe and created the initial fluctuations. After inflation, the universe was filled with a hot, dense plasma of particles and radiation, which continued to expand and cool. As it cooled, particles combined to form protons, neutrons, and eventually hydrogen and helium nuclei in the process of Big Bang nucleosynthesis. After about 3 minutes, the universe had cooled enough that nucleosynthesis ended, leaving a mix of hydrogen, helium, and trace amounts of lithium, the primordial elements. The universe continued to expand and cool, remaining ionized and opaque to light for the next few 100,000 years. At a redshift of about 1,000, when the universe was about 380,000 years old, it cooled enough for electrons and nuclei to combine into neutral atoms, a process called recombination. At this moment, the universe became transparent, and light could travel freely through space. This light is the cosmic microwave background, the oldest light we can observe, a snapshot of the universe at the moment of recombination, showing the tiny fluctuations in density that would later grow into the structure we see today. After recombination, the universe entered the Dark Ages, a period when no stars had yet formed, and the universe was filled with neutral hydrogen, dark and cold. Gravity began to pull matter together, forming the first dark matter halos, and within these halos, gas began to collapse and cool, eventually forming the first stars and galaxies. This epoch, called cosmic dawn, occurred a few 100 million years after the Big Bang, at redshifts around 20 or 30. The first stars were massive, hot, and short-lived, and they ionized the surrounding gas with their intense ultraviolet radiation. As more stars and galaxies formed, the ionizing radiation spread, gradually reionizing the entire universe, a process that took several 100 million years and was complete by a redshift of about 6, roughly a billion years after the Big Bang. The epoch of reionization is a critical period in cosmic history, marking the transition from a neutral universe to an ionized one, and it is closely tied to the formation of the first galaxies and the growth of large-scale structure. The wall observed by Webb exists at a redshift after reionization was complete, meaning the universe was already ionized and transparent, and galaxies had been forming for hundreds of millions to a billion years or more. From reionization onward, the universe continued to evolve, with galaxies merging, growing, and organizing into the cosmic web. Star formation peaked at a redshift of about 2 or 3, around 3 to 4 billion years after the Big Bang, when the universe was forming stars at the highest rate in its history. This epoch is sometimes called cosmic noon, the peak of cosmic activity, when galaxies were most active, when quasars were most luminous, and when the large-scale structure was rapidly assembling. The wall observed by Webb likely dates to this epoch, a time of vigorous structure formation, when walls and filaments were emerging from the initial density fluctuations and galaxies were forming and evolving within them. After cosmic noon, star formation began to decline, dark energy became more dominant, and the universe entered a phase of slower evolution, leading to the quiescent, mature structures we observe in the nearby universe today. The wall, observed at cosmic noon, provides a window into this peak epoch, a time when the processes shaping the universe were most active and most dramatic. Let us explore the implications of the wall for the dark sector, the components of the universe that do not emit light, namely dark matter and dark energy. Dark matter is inferred from its gravitational effects on visible matter, on the rotation curves of galaxies, on the motions of galaxies in clusters, on the gravitational lensing of light by massive structures, and on the large-scale structure of the universe. Despite decades of effort, dark matter has not been detected directly, and its nature remains one of the biggest mysteries in physics. The leading candidates are weakly interacting massive particles, WIMPs, but experiments searching for WIMPs have not found them. Other candidates include axions, sterile neutrinos, and primordial black holes, each with different properties and predictions. The distribution of dark matter on large scales, as traced by the cosmic web and structures like the wall, provides clues to its nature. If dark matter is cold, meaning the particles move slowly, it clusters on all scales, from small halos to large filaments. If dark matter is warm, meaning the particles move faster, it does not cluster as strongly on small scales, smoothing out the smallest structures. By measuring the abundance and properties of small-scale structure within the wall, such as dwarf galaxies or subhalos, astronomers can constrain the temperature of dark matter and test different particle physics models. The wall, as a large-scale structure, is less sensitive to the details of dark matter physics, but it still provides a consistency check, ensuring that the large-scale distribution is compatible with the small-scale observations and with the overall cosmological model. Dark energy is even more mysterious. It is the component driving the accelerated expansion of the universe, and it accounts for about 68% of the total energy content of the universe. The simplest explanation is the cosmological constant, a constant energy density associated with empty space with an equation of state parameter W equals -1. The cosmological constant is consistent with current observations, but it raises profound questions about why its value is so small, why it is not zero, and why it is comparable to the matter density at the present epoch, a coincidence called the cosmic coincidence problem. Alternative models of dark energy include quintessence, a dynamical field with an equation of state that changes over time, and modified gravity theories where the acceleration is not due to dark energy but to a modification of general relativity on large scales. The wall provides a test of dark energy and modified gravity by measuring the growth rate of structure at its redshift. The growth rate depends on the expansion history and the strength of gravity, both of which are affected by dark energy. If the wall is more or less prominent than predicted by the cosmological constant model, it could indicate that dark energy is not a cosmological constant, that its equation of state differs from -1, or that gravity is modified. Precise measurements of the wall's mass, size, and correlation with other structures can distinguish between these possibilities and provide constraints on dark energy models. Let us now consider the role of simulations in understanding the wall. Modern cosmology relies heavily on numerical simulations to predict the formation and evolution of structure. These simulations start with initial conditions based on the observed power spectrum of fluctuations, typically derived from the cosmic microwave background, and then evolve the matter distribution forward in time using the equations of gravity and hydrodynamics. Dark matter is treated as collisionless particles, evolved using n-body techniques that compute the gravitational forces between millions or billions of particles. Baryonic matter, gas and stars, is treated with hydrodynamical codes that solve the equations of fluid dynamics, including processes like gas cooling, star formation, supernova feedback, and black hole growth. The largest simulations, such as the Millennium Simulation, the Illustra Simulation, and the Eagle Simulation, have volumes comparable to the observable universe and resolution sufficient to resolve individual galaxies and halos. These simulations produce synthetic universes that can be compared directly with observations, allowing astronomers to test their models and understand the physical processes shaping the universe. The wall observed by Webb can be compared with structures in simulations at similar redshifts. By identifying walls in the simulation and measuring their properties, astronomers can determine whether the observed wall is typical, rare, or anomalous, and they can explore what physical conditions and parameters are required to produce walls of the observed size and coherence. Simulations also allow astronomers to make predictions that can be tested with future observations. For example, simulations can predict the velocity structure within the wall, the distribution of galaxy masses and star formation rates, the presence of diffuse gas, and the probability of finding rare objects like quasars or massive clusters. By comparing these predictions with observations from Webb and other telescopes, astronomers can validate the simulations, refine the input physics, and improve their models. Discrepancies between simulations and observations can point to missing physics, incorrect assumptions, or new phenomena that need to be included. The wall, as a large-scale structure with many observable properties, is an excellent test case for simulations, a complex, multi-scale system that challenges the models and pushes the limits of computational cosmology. The discovery of the wall by Webb thus not only expands our observational knowledge but also drives the development of better theoretical models and more realistic simulations. Let us explore the connection between the wall and the intergalactic medium in greater detail. The intergalactic medium is the gas that fills the space between galaxies, primarily hydrogen, with traces of helium and heavier elements. This gas is the reservoir from which galaxies form, and it is also the repository of gas expelled from galaxies by winds and outflows. The intergalactic medium is mostly ionized, kept that way by ultraviolet radiation from stars and quasars. Its temperature ranges from 10,000 to 1,000,000 degrees, depending on the density and the history of heating and cooling. The distribution of the intergalactic medium traces the large-scale structure, with higher densities along filaments and walls and lower densities in voids. The wall observed by Webb is associated with an overdensity of gas, a region where the intergalactic medium is denser and possibly hotter than average. This gas can be detected through its absorption of light from background sources, creating the Lyman alpha forest, a series of absorption lines in the spectra of distant quasars. Each absorption line corresponds to a cloud of neutral hydrogen along the line of sight, and the redshift of the line tells us the distance to the cloud. By measuring the distribution of Lyman alpha absorption lines toward quasars behind the wall, astronomers can map the gas distribution within and around the wall, measuring its density, temperature, and velocity. This provides a complementary view of the wall, one that traces the baryonic matter directly rather than inferring it from the galaxies. The intergalactic medium also plays a role in galaxy evolution. Galaxies accrete gas from the intergalactic medium, fueling star formation and growth. This accretion can occur through cold flows, streams of cool gas that penetrate deep into dark matter halos along filaments, delivering fresh gas to galaxies efficiently. Cold flows are thought to be important at high redshifts, when halos were less massive and less able to shock heat in falling gas. As halos grow and clusters form, the gas in the intergalactic medium is shock-heated to high temperatures, creating a hot halo that prevents cold gas from reaching the galaxy, quenching star formation. The wall, as a region of intermediate density, is a transition zone where cold flows and hot halos coexist, where some galaxies are still accreting gas and forming stars while others are beginning to be quenched by their environment. By studying the star formation rates and gas content of galaxies in the wall, and correlating them with the properties of the intergalactic medium, astronomers can learn about the interplay between galaxies and their environment, the mechanisms that regulate star formation, and the evolution of the galaxy population over cosmic time. The wall also affects the propagation of light through the universe. Gravitational lensing, the bending of light by mass, is strongest around massive structures like clusters, but it also occurs on larger scales due to the cumulative effect of all the matter along the line of sight. This is called weak gravitational lensing, and it distorts the shapes of distant galaxies slightly, creating a statistical signal that can be measured by averaging over many galaxies. The wall, as a massive structure extending across the sky, contributes to the weak lensing signal, and its effect can be detected and measured. By analyzing the shapes of background galaxies, astronomers can map the distribution of mass in the wall, including both the visible matter, the galaxies, and the dark matter, which dominates the mass. Weak lensing provides a direct measurement of the total mass independent of the properties of the galaxies or the gas, and it is a powerful tool for studying large-scale structure. The mass measured by weak lensing can be compared with the mass inferred from the galaxies and from the dynamics, providing a consistency check and a test of our understanding of the mass distribution. Let us now consider the wall in the context of multi-messenger astronomy. Traditionally, astronomy has been conducted with light, electromagnetic radiation at various wavelengths. In recent years, new messengers have become available, including gravitational waves, neutrinos, and cosmic rays, opening new windows on the universe. Gravitational waves, ripples in space-time produced by the acceleration of massive objects, have been detected from merging black holes and neutron stars, providing information about the most violent events in the universe. Neutrinos, nearly massless particles produced in nuclear reactions, have been detected from the Sun, from supernovae, and from extragalactic sources, carrying information about processes deep inside stars and other objects. Cosmic rays, high-energy particles accelerating to near light speed, have been detected for over a century, but their sources remain mysterious. The wall, as a large-scale structure, is not a direct source of gravitational waves, neutrinos, or cosmic rays in the way that compact objects like black holes or supernovae are, but it is part of the environment in which these sources exist and evolve. Massive galaxies in the wall may host supermassive black holes that merge, producing gravitational waves. Star formation in the wall produces supernovae, which emit neutrinos and accelerate cosmic rays. By correlating the positions of multi-messenger sources with the large-scale structure, astronomers can learn about the connection between structure and extreme events, the role of environment in triggering mergers and starbursts, and the propagation of cosmic rays and neutrinos through the intergalactic medium. The discovery of the wall also highlights the importance of large surveys and big data in modern astronomy. Webb is conducting surveys that image and spectrally analyze thousands of galaxies, producing datasets that are too large to analyze manually. Machine learning and artificial intelligence are increasingly used to process these data, identify patterns, classify objects, and extract scientific information. The discovery of the wall likely involved automated algorithms that flagged the clustering of galaxies at similar redshifts, prompting follow-up analysis to confirm the structure and measure its properties. As surveys grow larger and data volumes increase, the role of automated methods will become even more important, enabling discoveries that would be impossible with traditional techniques. At the same time, automated methods must be carefully validated to ensure they do not introduce biases or false positives. The wall represents a discovery at the intersection of cutting-edge observation technology, large-scale surveys, and advanced data analysis, a testament to the power of modern astronomy to explore the universe at scales and distances that were unimaginable a generation ago. Let us explore the cultural and philosophical implications of discovering a wall of galaxies. The scale of the universe has always inspired awe and wonder. From ancient civilizations who saw the stars as gods or as a celestial sphere surrounding the Earth, to the Copernican revolution that displaced Earth from the center, to the discovery of galaxies beyond our own, and the realization that the universe is vastly larger than our galaxy. Each step in expanding our cosmic horizons has reshaped our understanding of our place in the universe, humbling us with the recognition of our smallness and the vastness of space and time. The wall observed by Webb is another such step, a structure so large that it challenges our intuition, a coherent feature extending across hundreds of millions of light-years, containing thousands of galaxies, each a system of billions of stars, each potentially host to countless planets. The wall is not just a scientific curiosity, it is a reminder of the scale of the cosmos, the depth of time, and the intricate architecture of the universe, all of which inspire philosophical reflection on existence, purpose, and the nature of reality. From a scientific perspective, the wall is evidence of order emerging from chaos, of structure arising from simple initial conditions and universal physical laws. The universe began in a state of near-perfect uniformity, with tiny fluctuations imprinted by quantum mechanics and inflation. From these humble seeds, gravity and time have sculpted a universe of breathtaking complexity, a cosmic web of galaxies, a hierarchy of structures spanning scales from planets to superclusters. The wall is a manifestation of this process, a frozen moment in the evolution of structure, visible to us because light travels at a finite speed and the universe is transparent. By observing the wall, we are witnessing the universe's history, seeing the past as it happened billions of years ago, and learning about the processes that shaped the present. This connection between observation and history, between light and time, is one of the most profound aspects of astronomy, allowing us to study not just where things are but when they were, building a narrative of cosmic evolution that spans from the Big Bang to the present and beyond. The wall also raises questions about the uniqueness of our own location in the universe. We observe the wall from Earth, from within the Milky Way, from a particular place and time in cosmic history. The structure we see is partly a reflection of where we are and when we are observing. Had we been located elsewhere, we would see a different wall, a different portion of the cosmic web, a different arrangement of galaxies. The universe is the same everywhere on average, but locally it varies, and our observations are always local, always limited by our position in the light cone, accessible to us. This raises the question of how representative our observations are, whether the wall we see is typical or unusual, and whether our models derived from observations of our local universe apply everywhere and at all times. The cosmological principle assumes that the universe is homogeneous and isotropic, but structures like the wall remind us that this is only true on average, and that on smaller scales the universe is highly inhomogeneous, full of structure and variation. Understanding the wall, then, requires not just analyzing its properties, but understanding its place in the larger cosmic context, its typicality, and its relationship to the rest of the universe. Let us return to the technical details of the observation and consider the wavelength coverage and spectral features used to identify the wall. Webb observes in the infrared, specifically in the near-infrared from about 0.6 to 5 microns with NIR-CAM and NER-SPEC, and in the mid-infrared from 5 to 28 microns with MIRI. The redshift of the wall shifts rest frame optical and ultraviolet light into these infrared bands. For example, the Lyman alpha line, a prominent emission line of hydrogen at 121 nanometers in the rest frame, is shifted into the near-infrared at redshifts above about 0 to 2. At a redshift of 2, Lyman alpha appears at about 360 nanometers times 3, or roughly 1 micron, well within Webb's sensitivity range. Other lines, such as the Balmer lines of hydrogen, the oxygen lines, and the carbon lines, also shift into the infrared and can be detected by Webb. By identifying these lines and measuring their wavelengths, astronomers determine the redshift of each galaxy with high precision, building up the three-dimensional map that reveals the wall. The strength and ratios of the lines also provide information about the physical conditions in the galaxies, the temperature and density of the gas, the metallicity, the ionization state, and the presence of active galactic nuclei or starbursts. This spectral information is crucial for understanding not just where the galaxies are, but what they are, how they are evolving. The multi-wavelength approach, combining Webb's infrared observations with data from other telescopes at other wavelengths, enhances the science. Optical telescopes like Hubble provide high-resolution images in the rest frame ultraviolet for high-redshift galaxies, revealing the morphology and structure. Radio telescopes can detect emission from neutral hydrogen and molecular gas, tracing the fuel for star formation. X-ray telescopes can detect hot gas in clusters and emission from active galactic nuclei. Submillimeter telescopes detect dust emission, revealing obscured star formation. By combining data from all these wavelengths, astronomers build a complete picture of the wall, understanding not just the distribution of galaxies but their properties, their environments, and their interactions. This multi-wavelength approach is essential in modern astronomy, where no single telescope can provide all the information needed to understand complex systems like the wall. Let us also consider the role of citizen science and public engagement in discoveries like the wall. While professional astronomers conduct the observations, process the data, and publish the results, the public plays an important role in supporting astronomy, funding missions through taxes, and engaging with the science. Projects like Galaxy Zoo have shown that volunteers can contribute to science by classifying galaxies, identifying features, and flagging unusual objects in large datasets. The discovery of the wall could inspire similar projects, where volunteers help analyze Webb data, search for structures, or verify redshifts. Public engagement also includes education and outreach, communicating the significance of discoveries, explaining the science in accessible terms, and inspiring the next generation of scientists. The wall, with its scale and visual appeal, is an ideal subject for outreach, a concrete example of the universe's grandeur that can capture the imagination and convey the excitement of astronomical discovery. The wall also intersects with questions about the future of the universe. We have discussed its formation and evolution in the past, but what will happen to it in the future? The universe is expanding, and the expansion is accelerating due to dark energy. Over time, the wall will continue to evolve, its galaxies will continue to age, star formation will decline and eventually stop as gas is exhausted or removed. The galaxies will fade as their stars die, becoming dimmer and redder. The wall itself will expand with the universe, the distances between galaxies increasing, the structure diluting. In the far future, billions of years from now, the wall will be less distinct, its galaxies more separated, and the cosmic web will be stretched and thinned by the accelerating expansion. Eventually, in the extreme far future, trillions of years from now, the expansion may carry galaxies beyond each other's horizons, making them causally disconnected, unable to interact or even observe each other. The wall, like all structures, will dissolve into isolation, its coherence lost to the relentless expansion. This fate, the heat death of the universe, is the ultimate consequence of dark energy domination, a future where the universe becomes cold, dark, and empty, with no structure, no stars, no life. Understanding the wall and the large-scale structure of the present universe is therefore also understanding the transient nature of cosmic structure. A brief epoch in the history of the universe when gravity could assemble matter into beautiful, complex patterns before expansion and entropy erased them. The discovery of the wall is part of a broader effort to map the universe in 3 dimensions, to understand its structure and evolution on all scales. Webb is one tool in this effort, joined by ground-based surveys, other space missions, and multi-wavelength observations. The goal is to build a comprehensive model of the universe, from the smallest particles to the largest structures, from the Big Bang to the far future, a model that explains all observations and makes testable predictions. The wall is a piece of this puzzle, a data point in the distribution of matter, a test of our models, and a window into the processes that shaped the universe. Each discovery, each observation, adds to our understanding, refining the model, constraining the parameters, and sometimes revealing surprises that challenge our assumptions and drive new research. The wall, with its size, coherence, and high redshift, is one such surprise, a structure that pushes the boundaries of what we expect and motivates deeper investigations into the nature of cosmic structure and its origins. Let us now reflect on the technological achievement represented by Webb and its ability to detect the wall. Webb is the product of decades of planning, engineering, and international collaboration. Its mirror, 6.5 meters in diameter, is the largest ever launched into space, composed of 18 hexagonal segments that fold for launch and unfold and align in space. Its instruments are cooled to near absolute zero to reduce thermal noise, allowing them to detect faint infrared signals. Its orbit, at the second Lagrange point, 1.5 million kilometers from Earth, provides a stable, cold environment and a clear view of the sky. The telescope's design, construction, and deployment required solving countless technical challenges, from the folding mirror to the tennis court-sized sunshield to the precise alignment of optics. The success of Webb is a testament to human ingenuity, collaboration, and persistence, a demonstration of what can be achieved when scientists, engineers, and institutions work together toward a common goal. The discovery of the wall is a return on this investment, a scientific payoff that justifies the effort and expense, and an inspiration for future missions. The wall also prompts us to think about the limits of observation. Webb is powerful, but it is not unlimited. It cannot see arbitrarily far, detect arbitrarily faint objects, or resolve arbitrarily small details. There are limits set by the size of the mirror, the sensitivity of the detectors, the background light from the sky, and the finite time available for observations. Beyond a certain redshift, galaxies become too faint to detect even with Webb. The most distant galaxies observed by Webb are at redshifts around 10 or more, seen as they were a few 100 million years after the Big Bang. Beyond redshift 20 or so, the light from the first stars and galaxies becomes too weak, and the universe enters an epoch that may be forever inaccessible to direct observation with light. The wall, at a redshift of perhaps 2 or 3, is well within Webb's range, but it represents a snapshot of the universe at a specific epoch, and there are other epochs, other structures, that we cannot observe directly. Understanding the full history of the universe requires not just observation, but also theory, models, and inference, connecting the dots between the epochs we can see and extrapolating to the times and places we cannot. Let us explore the possibility that the wall is not unique, that there are other such structures in the universe, perhaps many of them. If the wall is a natural consequence of the initial density fluctuations and the processes of gravitational collapse, we would expect similar structures to exist wherever the conditions were right. The universe is large, and the volume we can observe is only a tiny fraction of the entire universe, which may be infinite. Within the observable universe, there may be many walls, filaments, and superclusters of similar or greater size, each a realization of the same statistical process, each shaped by the same physical laws. Surveys like the Sloan Digital Sky Survey have found numerous large-scale structures in the nearby universe, and as Webb and other telescopes probe deeper, we can expect to find more at higher redshifts. The wall observed by Webb may be the first of many such discoveries, each contributing to our understanding of structure formation and the statistics of the cosmic web. The more walls we find, the better we can characterize their properties, measure their abundance, and test our models. A single wall is interesting, but a population of walls is science, allowing statistical analysis and robust conclusions. The wall also invites comparison with simulations not just for validation but for discovery. Simulations can predict features and correlations that are difficult to observe directly, such as the velocity field, the distribution of dark matter, or the presence of rare objects. By comparing simulations with the observed wall, astronomers can identify features to look for, design follow-up observations, and maximize the scientific return. For example, simulations might predict that the wall should host a certain number of massive clusters, or that it should be associated with a particular pattern in the cosmic microwave background due to the Sunyaev-Zeldovich effect, where hot gas in clusters distorts the microwave background photons. Observing these predicted features would provide additional confirmation of the wall's properties and validate the simulations. Conversely, if the observations do not match the predictions, it suggests that the simulations are missing something, prompting revisions and improvements. The wall's discovery also has implications for the future of cosmology and the next generation of telescopes. Webb will eventually be succeeded by even more powerful observatories, both in space and on the ground. Proposed missions like the Habitable Worlds Observatory, the Lynx X-ray Observatory, and large ground-based telescopes like the Extremely Large Telescope and the 30-meter telescope will push the frontiers further, detecting fainter objects, resolving smaller details, and probing earlier epochs. The wall observed by Webb will be studied in even greater depth by these future instruments, with higher spectral resolution, larger samples of galaxies, and multi-wavelength coverage. The science of large-scale structure will continue to advance, driven by better observations, better simulations, and better theory, leading to a deeper understanding of the universe's architecture and evolution. The philosophical dimension of the wall extends to questions about the nature of time and causality in cosmology. When we observe the wall, we are seeing light that has traveled for billions of years, light that left the galaxies when the universe was younger, when the structures were forming, when stars were being born at a furious rate. The galaxies we see are not as they are now, but as they were then. In the time since the light left, those galaxies have continued to evolve. Their stars have aged, new stars have formed, and the structure has grown and changed. We cannot see the current state of the wall. It is hidden from us by the light travel time. This means that our observations are always historical, always looking into the past, and the further we look, the further back we see. Cosmology is therefore a historical science, reconstructing the past from the light that has reached us, building a narrative of cosmic evolution by stitching together observations from different distances and different times. The wall is a chapter in this narrative, a snapshot from cosmic noon, a piece of the history of structure formation that helps us understand how the universe evolved from simplicity to complexity. Let us consider the wall in relation to the anthropic principle, the idea that the properties of the universe are constrained by the requirement that it must be able to support observers like us. The wall, and a large-scale structure in general, exists because the initial fluctuations had a certain amplitude, because the matter content was a certain value, because the cosmological constant was a certain magnitude. If any of these parameters were very different, the universe might not have formed stars and galaxies at all, or it might have formed only black holes, or it might have remained forever uniform. The fact that we observe a universe with structure, with walls and galaxies and stars and planets, is in part a selection effect. We can only exist in a universe that allows for the formation of such structures. This does not mean the wall is designed for us, but it does mean that the parameters that allow the wall to exist are the same parameters that allow life to exist, and any observers in the universe will find themselves in a universe capable of forming structure. The anthropic principle is controversial, and it does not provide specific predictions, but it offers a perspective on why the universe is the way it is, a reminder that our existence is contingent on the properties of the cosmos. The wall's observation also touches on the question of reproducibility and verification in astronomy. Unlike laboratory experiments, astronomical observations cannot be repeated in the same way. The universe evolves, objects move, and we cannot go back in time to re-observe the same event. However, we can observe similar objects at similar distances, building up a statistical sample that tests our models. The wall can be verified by independent observations, by other telescopes, by different methods, and by checking for consistency in the data. Multiple spectra of the same galaxy should give the same redshift. The distribution of galaxies should be consistent across different regions of the wall. The properties of the galaxies should correlate in expected ways. These consistency checks are essential for ensuring that the discovery is real and not an artifact of the data or the analysis. Once verified, the wall becomes part of the established body of knowledge, a reference point for future studies, and a benchmark for testing theories. The wall, as a structure extending across the sky, also raises questions about projection and the three-dimensional nature of space. When we observe the sky, we see two dimensions: right ascension and declination, the celestial coordinates analogous to longitude and latitude on Earth. The third dimension, distance, is inferred from redshift or other distance indicators. The wall appears as a concentration of galaxies in a particular region of the sky, but without redshift information, we cannot tell if it is a single structure or a projection of multiple unrelated structures along the line of sight. Redshift surveys provide the third dimension, allowing us to map the structure in 3 dimensions and confirm that the wall is a coherent feature. not a chance alignment. This three-dimensional mapping is one of the great achievements of modern cosmology, transforming our view of the universe from a two-dimensional celestial sphere to a three-dimensional cosmic web, revealing the true architecture of the cosmos. Let us also consider the aesthetic dimension of the wall. Visualizations of the cosmic web, whether from observations or simulations, are strikingly beautiful, intricate networks of filaments and nodes, vast voids and dense clusters, all organized by gravity into patterns that resemble neural networks, city lights at night, or abstract art. The wall, as part of this web, contributes to the visual splendor of the universe, a reminder that nature creates beauty on all scales, from the microscopic to the cosmic. This beauty is not merely superficial. It reflects the underlying order and symmetry of physical laws, the elegance of mathematics, and the simplicity of the fundamental principles that govern the universe. The fact that the universe is comprehensible, that it follows laws we can discover and express in equations, is itself remarkable, and the beauty of structures like the wall is a manifestation of this comprehensibility, a visual expression of the laws of physics. The discovery of the wall is also a story of collaboration. Modern astronomy is a global enterprise involving thousands of scientists from many countries, sharing data, ideas, and resources. Webb is a mission of NASA, the European Space Agency, and the Canadian Space Agency with contributions from institutions around the world. The data from Webb are publicly available, allowing researchers everywhere to access and analyze them. The discovery of the wall likely involved a team of astronomers, from graduate students to senior researchers, each contributing expertise in observations, data processing, analysis, and interpretation. Science is a collective endeavor built on the work of many individuals, and the discovery of the wall is the result of this collective effort, a testament to the power of collaboration and the shared human quest to understand the universe. The wall also connects to questions about the ultimate fate of information. In the far future, as the universe expands and galaxies recede beyond the horizon, the information about distant structures will be lost, unreachable even in principle. The light from the wall and from all distant galaxies will eventually be redshifted to such long wavelengths that it becomes undetectable. New galaxies forming beyond the horizon will never be observable to us. In this sense, the universe we can observe is shrinking over time, even as the physical universe expands. The wall, observed now, is a snapshot that will remain accessible for a finite time, a window on the universe's structure that will eventually close as expansion carries the structure beyond our reach. This raises questions about the nature of reality and observation. Does the wall still exist if we cannot observe it? Do structures beyond the horizon have the same reality as those within it? These are questions at the boundary of physics and philosophy, where the limits of observation meet the nature of existence. Let us reflect on the process of scientific discovery itself, using the wall as an example. Discovery in astronomy often begins with a question or a hypothesis, followed by the design of observations to test the hypothesis. Sometimes, however, discoveries are serendipitous, emerging unexpectedly from data collected for other purposes. The wall may have been discovered either way, either as the result of a targeted search for large-scale structures at high redshift, or as a surprise in a deep-field survey. Regardless of how it was found, the discovery process involves several stages: detection, confirmation, characterization, and interpretation. Detection is the initial observation, the signal that stands out from the noise. Confirmation involves independent checks, repeat observations, and consistency tests to ensure the signal is real. Characterization involves measuring the properties of the structure, its size, mass, redshift distribution, and galaxy population. Interpretation involves understanding what the structure tells us about the universe, fitting it into the larger framework of cosmology, and drawing conclusions about structure formation, dark matter, dark energy, and the initial conditions. Each stage requires different skills and tools, from observational astronomy to data analysis to theoretical modeling, and each stage builds on the previous one, advancing our knowledge step by step. The wall also reminds us of the provisional nature of scientific knowledge. What we know about the universe today is based on current observations and current models, but both are subject to revision as new data and new ideas emerge. The wall, as a new discovery, may challenge existing models, prompting revisions or refinements. Alternatively, it may confirm the models, strengthening our confidence in them. Either way, it contributes to the ongoing process of building and testing scientific knowledge, a process that is never complete but always advancing. Science is not a collection of fixed facts but a dynamic enterprise, constantly evolving as we learn more about the world. The discovery of the wall is a step in this evolution, a piece of new knowledge that will be integrated into the larger body of cosmology, influencing future research and shaping our understanding of the universe. The wall's existence also has implications for the search for life beyond Earth. While the wall itself is not directly related to the question of life, it is part of the cosmic environment in which life arises. Galaxies within the wall contain stars, and those stars have planets, and some of those planets may be habitable, with conditions suitable for life. The abundance and distribution of galaxies, the rate of star formation, and the availability of heavy elements, all of which are influenced by large-scale structure, affect the likelihood of life emerging. Regions of the universe with more structure, more galaxies, and more star formation may be more conducive to the origin of life, simply because there are more opportunities, more planets, and more places for life to start. The wall, as a concentration of galaxies, may be a region where life is more common, though this is highly speculative and depends on many unknowns. Regardless, the study of large-scale structure in the cosmic web provides context for astrobiology, the study of life in the universe, by mapping the distribution of potential habitats and understanding the conditions that favor or hinder the emergence of life. The wall also connects to the concept of cosmic variance, which we mentioned earlier, in a deeper way. Cosmic variance arises because we observe only one realization of the stochastic process that generates structure. The initial fluctuations are random, drawn from a probability distribution, and the structures that form depend on the specific realization of those fluctuations. If we could observe many universes, we could average over the realizations and reduce the statistical uncertainty, but we can only observe our own universe. This means that our measurements of large-scale structure are subject to irreducible uncertainty, especially on the largest scales where the number of independent samples is small. The wall represents a significant fraction of the observable volume at its redshift, and its properties contribute to the cosmic variance in measurements of structure on that scale. If we measure the abundance of walls, or their typical sizes, using only the observable universe, the result will have significant uncertainty due to cosmic variance. This is a fundamental limitation in cosmology, one that can only be overcome by observing to larger distances, increasing the volume sampled, or by combining observations with theoretical priors from models and simulations. Let us explore the possibility that the wall may be traceable across multiple wavelengths and observables, creating a multidimensional dataset that enhances our understanding. The galaxies within the wall emit light at all wavelengths, from radio to gamma rays, depending on their properties. Radio observations can detect synchrotron emission from relativistic electrons, tracing supernovae, pulsars, and active galactic nuclei. Infrared observations, like those from Webb, reveal stars and dust. Optical observations show the stellar populations and structures. Ultraviolet observations trace hot, young stars and star-forming regions. X-ray observations detect hot gas and accreting black holes. By combining all these wavelengths, astronomers can build a complete picture of the energy budget, the physical processes, and the environmental conditions within the wall. Additionally, the wall may be detectable in the cosmic microwave background through secondary effects, like the integrated Sachs-Wolf effect, where photons gain or lose energy as they traverse large-scale structures, creating hot and cold spots in the microwave background correlated with the distribution of matter. Detecting such a signal would provide an independent confirmation of the wall's existence and its mass. The wall also invites us to think about the concept of emergence in complex systems. Emergence refers to the appearance of new properties or patterns at higher levels of organization that are not present at lower levels. In the universe, atoms do not have the property of being a galaxy, but when atoms are organized in vast numbers under the influence of gravity, galaxies emerge. Similarly, galaxies do not individually have the property of forming a wall, but when galaxies are distributed according to the large-scale density field, walls emerge as coherent structures. The wall is an emergent phenomenon, a pattern that arises from the collective behavior of billions of galaxies, each responding to the gravitational field created by all the others. Understanding emergence in cosmology requires understanding both the microscopic level, the individual galaxies and their properties, and the macroscopic level, the large-scale structure and its statistics. The wall is a bridge between these levels, a structure that emerges from the micro and reveals the macro, illustrating the multi-scale nature of the universe. The wall may also serve as a probe of primordial non-Gaussianity, deviations from the Gaussianities of friends. In the simplest inflationary models, the fluctuations are perfectly Gaussian, meaning their statistical properties are completely described by the power spectrum, and there are no higher-order correlations. However, more complex inflationary models, or alternatives to inflation, can produce non-Gaussianity, where 3-point or higher-order correlations are non-zero. Non-Gaussianity would affect the abundance and properties of large-scale structures like the wall, potentially making them more common or more massive than predicted by Gaussian models. By measuring the statistics of walls and comparing them with predictions from Gaussian and non-Gaussian models, astronomers can constrain the level of primordial non-Gaussianity and learn about the physics of the very early universe. The wall, as a rare large-scale structure, is particularly sensitive to non-Gaussianity because non-Gaussian effects are most pronounced at the extremes of the distribution. Let us now turn to the human element in the discovery, the excitement and curiosity that drive scientists to explore the unknown. The discovery of the wall is not just a scientific achievement, but a human one. The result of years of preparation, countless hours of work, and the passion of individuals who dedicate their lives to understanding the universe. Astronomers who work on projects like this often describe the thrill of discovery, the moment when the data reveals something unexpected, when a pattern emerges that hints at a new understanding. The wall, when first detected in the data, would have prompted excitement, questions, and intense scrutiny. Is it real? How big is it? What does it mean? These questions drive the research, motivating deeper analysis, follow-up observations, and collaboration with colleagues. The discovery of the wall is a reminder that science is a human endeavor, driven by curiosity, creativity, and the desire to push the boundaries of knowledge. The wall also reflects the cultural importance of astronomy, the role that exploring the universe plays in human society. From ancient times, humans have looked at the sky and wondered about the stars, the planets, and the cosmos. Astronomy has shaped cultures, inspired mythologies, and driven technological innovation. The discovery of the wall, like all astronomical discoveries, enriches our cultural heritage, adding to the collective knowledge of humanity and inspiring future generations to look up, to wonder, and to explore. Astronomy is one of the few sciences that captures the public imagination on a large scale, and discoveries like the wall are opportunities to engage with the public, to share the excitement of science and to remind people of the beauty and mystery of the universe. The wall's discovery also has educational value, serving as a case study in cosmology, observational astronomy, and the scientific method. Students learning about the universe can study the wall as an example of large-scale structure, understanding how gravity shapes the distribution of matter, how observations are conducted, and how data are analyzed and interpreted. The wall can be used to teach concepts like redshift gravitational collapse, dark matter, and the cosmic web, providing a concrete example that makes abstract concepts more tangible. Education in astronomy not only trains future scientists but also promotes scientific literacy in the broader population, helping people understand how science works why it is valuable, and how it contributes to society. Let us consider the wall in the context of cosmic cartography, the effort to map the universe in detail, just as cartographers map the Earth, creating charts that show continents, mountains, rivers, and cities. Cosmologists map the universe, creating charts that show galaxies, clusters, filaments, and voids. The wall is a feature on these cosmic maps, a prominent structure that must be charted and understood. Mapping the universe is a monumental task, requiring observations of millions of galaxies, measurements of their positions and distances, and the construction of three-dimensional models. Projects like the Sloan Digital Sky Survey have made great progress in mapping the nearby universe, and Webb is extending these maps to greater distances and earlier times. The wall observed by Webb is a new feature on the cosmic map, expanding our knowledge of the universe's geography and adding detail to our understanding of its structure. As maps become more complete and more detailed, they enable new science, allowing researchers to identify patterns, test models, and make predictions about the universe's evolution. The wall also invites reflection on the limits of human cognition and our ability to comprehend the universe. The scale of the wall, hundreds of millions of light-years, is beyond human experience. We have no intuitive sense of such distances, no direct analogy in our everyday lives. A light-year, the distance light travels in a year, is already almost incomprehensibly large, about 9.5 trillion kilometers. The wall extends across hundreds of millions of such distances, a scale so vast that it defies visualization. Yet, through mathematics, through models, and through observations, we can understand the wall, describe its properties, and fit it into the larger framework of cosmology. This is the power of science, the ability to extend human understanding beyond the limits of direct experience, to comprehend phenomena that are too large, too small, too fast, or too slow for our senses. The wall is a testament to this power, a structure that we can know even though we cannot directly perceive it. The discovery of the wall also highlights the importance of serendipity in science. While many discoveries are the result of targeted searches and planned experiments, some of the most important discoveries happen by accident, when researchers notice something unexpected in their data. The wall may have been such a discovery, an unexpected feature that emerged from a deep field survey. Serendipity requires prepared minds, scientists who are alert to anomalies, who ask questions, and who follow up on unexpected results. It also requires open data sharing and collaboration, so that many eyes can examine the data and different perspectives can be brought to bear. The discovery of the wall, whether planned or serendipitous, exemplifies the scientific process at its best, a process that combines careful planning, rigorous analysis, and openness to the unexpected. Let us explore the implications of the wall for the concept of the observable universe. The observable universe is defined as the region of space from which light has had time to reach us since the Big Bang. It is a sphere centered on Earth, with a radius determined by the age of the universe and the speed of light, currently about 46.5 billion light-years in comoving coordinates, accounting for the expansion of space. The wall, observed at a redshift corresponding to billions of light-years, is well within the observable universe, but it is closer to the edge than to the center. As we observe greater distances, we approach the edge of the observable universe, the cosmic horizon beyond which we cannot see. The existence of the wall suggests that structure extends to large distances, perhaps all the way to the horizon and beyond, into the unobservable universe. If the universe is infinite, or much larger than the observable portion, then structures like the wall may be common throughout the entire cosmos. And what we observe is just a sample, a tiny piece of a much larger pattern. This raises questions about the global properties of the universe, the overall distribution of matter, and whether the observable universe is representative of the whole. The wall's discovery also connects to the question of the geometry of the universe. General relativity allows for different geometries depending on the total energy density. If the density is high enough, the universe is closed, finite, and curved, like a sphere, eventually collapsing in a big crunch. If the density is too low, the universe is open, infinite, and curved like a saddle, expanding forever. If the density is exactly critical, the universe is flat, infinite and Euclidean, also expanding forever. Observations of the cosmic microwave background indicate that the universe is very close to flat, with any curvature too small to measure. The distribution of large-scale structure, including walls like the one observed by Webb, provides an additional test of geometry. In a curved universe, the distribution and appearance of structures would be affected, altering the apparent sizes and separations of distant objects. The fact that the wall and other structures appear consistent with a flat geometry supports the conclusion from the microwave background and reinforces our understanding of the universe's overall shape. Let us consider the wall in the context of the multiverse hypothesis, the idea that our universe is one of many, each with different properties, different physical constants, and different histories. The multiverse is a speculative concept arising from certain interpretations of inflation and quantum mechanics, and it is controversial because it is difficult or impossible to test observationally. However, if the multiverse exists, the properties of our universe, including the presence of structures like the wall, may be explained by selection effects, by the fact that we can only exist in a universe with the right properties to support life and observers. The wall, and the large-scale structure in general, exists because the cosmological parameters in our universe allow for structure formation. In other universes within the multiverse, with different parameters, structures might not form at all, or they might form very differently. The multiverse provides a framework for understanding why the universe is the way it is, but it also raises profound questions about the nature of reality, the meaning of probability, and the role of observation in defining existence. The wall also invites us to think about the role of time in cosmology. Time in the universe is not absolute, but relative, dependent on the observer's frame of reference and the gravitational field. In general relativity, time is part of space-time, a four-dimensional fabric that is curved by mass and energy. On cosmological scales, we use cosmic time, a time coordinate synchronized with the expansion of the universe, marking the time since the Big Bang as measured by an observer, moving with the average expansion. The wall exists at a particular cosmic time corresponding to its redshift, a time when the universe was younger and the structure was forming. Observing the wall is observing the past, seeing the universe as it was at that cosmic time. Time in cosmology is thus intimately connected with observation, with distance, and with the expansion of space, creating a complex interplay between what we see and when it happened. The discovery of the wall is also a moment to appreciate the progress of astronomy over the centuries. From Galileo's first telescopic observations of the moons of Jupiter, to Hubble's discovery of the expanding universe, to the detection of the cosmic microwave background, to the mapping of the cosmic web, each generation of astronomers has built on the work of the past, using better tools and better ideas to push the frontiers of knowledge. Webb represents the latest step in this progression, a telescope that surpasses all previous instruments in its ability to observe the infrared universe, and the discovery of the wall is one of the first fruits of this new capability. Looking forward, we can anticipate that future telescopes will continue the progression, revealing even deeper secrets of the cosmos, perhaps discovering structures even larger than the wall, or phenomena we cannot yet imagine. The wall stands, therefore, as a testament to the universe's grandeur, to the power of human curiosity and ingenuity, and to the ongoing quest to understand the cosmos. It is a structure written in light and time, shaped by forces operating over billions of years across unimaginable distances. It challenges our models, inspires our imagination, and expands our knowledge. The wall is not the end of the story, but a new chapter, a discovery that opens new questions and new avenues of research. As astronomers continue to study the wall, as more data are collected, as simulations are refined, and as theories are tested, we will learn more about this remarkable structure and about the universe it inhabits. The wall is a reminder that the universe is vast, that it is full of wonders waiting to be discovered, and that the journey of exploration is far from over. Each observation, each discovery, each moment of understanding brings us closer to comprehending the cosmos. And the wall observed by James Webb is a shining example of that progress, a beacon illuminating the structure of the universe and our place within it.